Can I start now?
Yes, sir.
Yes, sir.
Okay, thank you. So in our previous lecture, we were discussing about the zero crossing and what are the various type of signals shown by the amplitude modulation, frequency modulation, and phase modulation. And we have also compared the three signals, one sinusoidal, another square wave, and the third one was the ever increasing signal. And we have compared the three signals corresponding to three amplitude techniques, modulation techniques, and we have discussed that the zero crossing results into a symmetric amplitude modulation signal, whereas the symmetricity breaks in case of frequency modulation and phase modulation for the zero crossing. So the zero crossing is a fault in case of frequency modulation and phase modulation, whereas the symmetric transition from positive to negative axis exists in case of amplitude modulation technique. Now continuing to the previous lecture, now let us discuss the one more way to represent this symmetricity in case of the frequency modulation, phase modulation, and amplitude modulation techniques. Now let us consider a sinusoidal frequency modulation process, and let us consider a message signal represented by Em cos 2 pi fmt. This is a pure sinusoidal signal, and we have a message signal here. This is our message signal, whose shape is similar to the sinusoidal signal. This is the reason 1 in which there is no amplitude of the message signal. So when this message signal is superimposed upon carrier, then in reason 1, there will be no change in the frequency of the carrier. When we have a rise from this region to this region, in second region we can say, so in this region the function is increasing. Function means modulating signals amplitude is increasing. So how to represent this increasing magnitude? This increasing magnitude is represented by change in frequency. And what will be the change in frequency in region 2? The frequency will increase. Now in region 2, the frequency decreases, amplitude decreases, and this again is represented by a change in frequency, and that change will be decrease in the frequency. Once again we have another reason in which signal amplitude is decreasing in the negative direction, and we can say it is increasing in the negative direction. So again the frequency will increase, and once again when it starts going from negative to positive axis, the frequency again increases. So this is the complete cycle. When no signal is applied, no modulating voltage or modulating signal, frequency means when the signal is increasing continuously up to a maximum point, the frequency change will be there and frequency will increase. Now the signal is start decreasing up to 0 and then further decrease up to minus maximum. So again in this region the frequency change, and frequency change is in the direction of decreasing frequency. Now once again from this point, this has started increasing up to 0. So once again in this region the frequency has started. Frequency modulation technique in which the change in modulating signals amplitude is represented in the form of change in frequency, contraction or expansion, we can say. High frequency or low frequency. Amplitude increasing, we are increasing towards higher frequency. Amplitude decreasing, we are moving towards lower frequency also. Similarly, In case of phase modulation, reason 1, where no voltage is applied, no modulating signal is applied, there will be no change in the phase. When signal is applied, signal is in the form of a sinusoid, it will reach to maximum, from maximum it will come to 0, from 0 it will go to maximum minus amplitude, and then from minus maximum amplitude it again comes to 0 and then positive, or repeated in this way. So when no signal is applied in this region, there is no modulation in the carrier wave, that is carrier wave frequency, phase, amplitude remains as it is. When modulating signal is applied in region 2, it goes from 0 to maximum, maximum to 0. So in this region, the change will be represented by the carrier wave. And in region 2, where maximum, region 3, where maximum amplitude has now become minimum amplitude. So for this, the compression exists, and again the change in the change according to the modulating voltage is again represented by a phase change. So the common thing here is, if there is no modulating signal applied, there will be no change in phase or frequency. If a modulating signal is applied, there will be change, and change will be in accordance with the message signal. It will represent the form of the message signal. That is, message signal goes from 0 to maximum, maximum to 0, 0 to minus negative maximum, from negative maxima to 0, and then repeat itself. So that change is represented by change in frequency of the carrier wave or phase of the carrier wave. Now let us talk about another type of wave. Let us say scare type of wave. In scare type of wave, again this is represented by compression, and correspondingly the high frequency region are those which are compressed, low frequency region are those which are expanded. High frequency region is represented because your message signal written by M has a maximum amplitude in this region, and our modulating signal has minimum amplitude in this region. So for region, let us say it is region 2, and let us say it is region 1. So in region 1, the amplitude is maximum, so frequencies are high and the carrier wave is compressed. The amplitude is in negative direction maximum, so carrier wave is expanded, stretched, and correspondingly there is change in frequency, which represents the shape or envelope of the modulating signal. Now in case of second figure, the phase modulation is again represented in the form of the envelope of the modulating signal. So again there will be regions of phase reversal or so, which will represent the region of maximum amplitude of the modulating signal, that is positive scare wave, and region where a reverse wave is represented. So again we can divide this phase modulation into two parts. Part 1, which will represent the up wave, scare wave, positive scare wave. Region 2, the reverse region, which is called as phase reversal, which represents the low phase part, which represents the negative envelope of the modulating signal. So this was all about the frequency modulation, phase modulation for the sinusoidal signals and the scare waves. Now let us compare the frequency modulation and phase modulation in one table. So point wise we will discuss them. First, the expression. The expression of the phase modulation as we see as common because this is the amplitude of the carrier, and this amplitude of the carrier we know does not change. Now what changes? The change will be in the form of this angular variation of sign. This angular variation of sign has two parts. Obviously, it have a carrier part which is represented by this term omega ct in both phase modulation and frequency modulation. The second term involves the modulating signal, which is MF means modulation index frequency modulation. MP again means modulation index for phase modulation. So the serial number 1 represents the modulating wave equation for frequency modulation and the phase modulation, and it has two parts. Part 1, which is VC, that is constant amplitude of the carrier wave, because we are not talking here of amplitude modulation, so amplitude will remain constant. Second, the theta part, which has further two parts. One part represents the carrier, another part represents the superposed modulating signal. Serial number 2, frequency deviation is proportional to the modulating voltage. Phase deviation is proportional to the modulating voltage. Now this deviation is represented in the form of an expression which is multiplied k times the modulating voltage amplitude, which we will discuss in the next lecture on narrowband FM and wideband FM. Point number 3, associated with the change in carrier frequency, there is some phase change. Associated with the change in phase, there is some change in frequency. Now this point is important. Why? Because corresponding to frequency there is some phase change, and corresponding to phase change there is frequency change. So it means we can derive the frequency modulation from phase modulation and phase modulation from frequency modulation. If you remember from our previous lecture, there we have discussed with the help of a block diagram that we can generate the phase modulation from frequency and frequency modulation from the phase modulation. Is screen visible?
Yes, sir.
Okay, some people were trying to join. I have to move back to the main page of the meeting. I have joined them. Next time, those who have joined late, please do not join late, and please do not write message or call me. Either join on time or leave the meeting. Please be particular about this, disciplined about this. I will not entertain next time those who are late, who are joining late. Okay, fourth point, MF is proportional to the modulating voltage as well as the modulating frequency. MP is the modulation index, which is related to the phase modulation technique. Fifth point, it is possible to receive FM on a PM receiver, and it is also possible to receive a PM on FM receiver. This is nothing but the third point, that we can generate the FM or PM from one another. So point number 3, point number 5 are same. Sixth point, noise immunity is always better as compared to AM. Amplitude of FM is constant, which you can see in the first point, that is VC is constant. It will remain constant for phase modulation as well. Signal to noise ratio is always better in PM. Signal to noise ratio is inferior to that of FM. Amplitude modulation has signal to noise ratio high. Why signal to noise ratio is high in AM? The reason is that there is disturbance or distortion or attenuation is in the modulating signal in amplitude modulation technique, whereas the extra noise, that is attenuation, distortion or disturbance in the superposed signal, is less in case of frequency modulation or phase modulation. So that's why the point number 8, the FM and PM always has better noise immunity as compared to amplitude modulation. FM is widely used, PM is used in some mobile systems. 9th point. 10th point, in FM the frequency deviation is proportional to the modulating voltage only. In PM the frequency deviation is proportional to the modulating voltage as well as modulating frequency. We will discuss about the frequency deviation in our next lecture, that is narrowband FM and wideband FM. for at present frequency deviation, you can simply say it is a product of the modulation index for phase or frequency multiplied to the maximum amplitude of the modulating signal. So in similar way, we can compare the frequency modulation and amplitude modulation also. This is the last slide for the today's lecture. Serial number 1, amplitude of the FM wave is constant. It is independent of the modulation index. But we know in case of amplitude modulation, the amplitude of the modulating voltage will change according to the message signal. So this is the major change in case of FM, PM or AM. Here the amplitude remains fixed in FM and PM, whereas the AM technique has change in amplitude of the modulating signal in accordance with the message signal. Second point, hence transmitted power remains constant because amplitude is remaining constant. Transmitted power is dependent upon the modulation index. All the transmitted power is useful in case of FM, whereas in AM all the power is not useful. It depends upon the type of technique we are using. Because we know double sideband suppressed carrier. In amplitude modulation technique, we have both bands. In double sideband suppressed carrier technique, we suppress the carrier. In single sideband, we suppress the carrier as well as we suppress one of the sideband. In vestigial sideband, to avoid the complexity in the circuitry, we take some vestige part from the lower band or the upper band. FM receivers are immune to noise, already discussed. Signal to noise ratio in FM and PM is very small as compared to AM. AM receivers are not immune to noise. They produce huge noise as compared to the FM and the PM signals. Fifth point, it is possible to decrease noise further by increasing deviation. Deviation, that is delta F is equal to K into EM, which we will discuss next time. Sixth, bandwidth is given by 2 times into the deviation of the frequency plus modulating frequency. Bandwidth is equal to twice the modulating frequency, highest frequency present in the message signal. Bandwidth is large in case of FM and PM, hence wide channels are required for FM-PM transmission. Bandwidth is much smaller as compared to FM or PM, so no wide channel requirement is there in case of amplitude modulation technique. Space wave is used for the propagation of the frequency modulation, so radius of transmission is limited to line of sight, means the transmission cannot cover large areas. Ground wave and sky wave propagation are used in case of amplitude modulation. I am discussing point number 8. So therefore, large areas are covered under the AM and large areas are covered as compared to the FM or PM. Point number 9. In case of FM, it is possible to operate several transmitters on same frequency. In amplitude modulation, this transmission of more channels at same frequency is not possible. 10th point, FM transmission and reception equipment are more complex. AM equipments are less complex. Last point, the number of sidebands having significant amplitudes depend upon the modulation index. Number of sidebands in amplitude modulation will be constant and equal to 2. So number of sidebands and modulation index in case of FM, PM and AM are different. In AM, the modulation index is around 1 or less than 1. Number of sidebands are 2 in AM, whereas in case of FM and PM, the modulation index is around 1 and can be more than 1, and even it can be hundreds of times greater than 1. The second thing is number of sidebands in case of FM are more than 2 possible. So due to number of sideband greater than 2 in FM and PM, it is possible to send more and more signals.